A lot of the control systems we work with are represented in block diagram form. So let's review block diagrams and some of the standard connections. Probably the simplest connection of two systems or two blocks is what's known as the cascade connection, or you might call this a series connection also. This is when you've got one system followed by another, and if we denote the input as x of t and the output of the combined system of y of t, the overall system transfer function is just the product of the individual transfer functions in this cascade form. So we could replace the two cascade blocks with a single system having a transfer function equal to h1 of s times h2 of s. And again, this is easy to derive this relationship in the Laplace transform domain. Call the output of the first system w, then w would be x of s times h1 of s, and y of s then would be w of s times h2 of s, and then algebraically combining those, we can see then that y of s is equal to x of s times the product of h1 of s and h2 of s. Another standard connection is a parallel connection of blocks, so where the two blocks have the same input. Again, we'll denote one system by its transfer function h1 of s. The second system has transfer function h2 of s, and then we're going to add the two outputs plus using a summer to produce a single output y. We can replace the two blocks as well as the summer with a single system whose transfer function is just the sum of the two transfer functions. And then for any given input, we will get the same output from this combined system as we would from this parallel system. And the final connection we'll look at is a feedback connection, which you'll see quite often in control systems. Here the input x comes into a summer. I'll use S-domain notation here, and then in negative feedback we subtract from the input feedback signal, and we have a feedback system is made up of two components: a feed forward component called g of s, which takes the difference between x and the feedback system, that's typically called E for error, the error signal, and then that produces y. And then y is fed back through another system called a feedback system. So we'll just tap off y here, and then the difference between this feedback system and x is produces our error signal. So algebraically we can work through this and directly solve for y in terms of x. It's worthwhile for you to go through this on your own. We can write the error signal is equal to x minus the feedback system, which is h times the feedback signal, which is h times y. And then from the feed forward system we have that y is equal to g times e. So our goal here is to actually eliminate e, so we have a direct expression involving only x and y. Well, here from this second expression I can solve for e, that's equal to y over g. Then taking this and plugging it into my first equation over here, then I'm going to get y over g is equal to x minus hy. Now I've got the desired expression involving only x and y and my transfer functions. So I'll combine my y terms on the left-hand side. I'll have 1 over g plus h is equal to x, and then writing this over a common denominator, I'll have y. I can write this as hg over g, so I'll have 1 plus hg all over g is equal to x. And then so finally I get my equivalent, or my relationship between y and x, which would be my equivalent system transfer function. It's g over 1 plus hg. And so I can replace this feedback system with an equivalent system whose transfer function is g over 1 plus hg to produce y. Just one final note. Due to loading effects, circuit connections do not always follow the block diagram connection rules. So, for example, if I've got a simple RC circuit with R1 here and C1 here, producing an output Y with input X, and then another RC circuit here with C2 and R2. And this first one is actually a low-pass filter. The second one would be a first-order high-pass filter. But let's assume that I wanted to connect the two together, and it's possible to do this to connect to create a bandpass in such a way that we can create a bandpass filter. We can solve for the transfer function of this first circuit. It's 1 over R1 C1 times 1 over S plus 1 over R1 C1, and the transfer function of the second filter is S over S plus 1 over R2 C2. Now if we connect them together, so here's my low pass filter, and then followed by my high pass filter. It would be nice if the transfer function of this combined system was equal to the product of H1 of S and H2 of S, but it is not. Okay, I'm not going to solve for that, but the reason is that the loading effect due to attaching the high pass filter to the low pass filter actually changes the transfer function of the low pass filter. So in general, this is not true. It's approximately true if the input impedance of the second stage is very high compared to the output impedance looking back into looking back into the first stage. Now this is true often when we implement first and second order filters using operational amplifiers, and in that case we can approximate an overall transfer function of a cascade of op-amp filters as the product of the individual transfer functions. But for passive circuits in general, you can't do that. You'd have to solve for the overall transfer function here of the connected circuit.